Okay. So today we will start with chapter 7. Okay, on properties of expectation. Okay. All right. We actually define expectation of a general random variable in chapter 4 before. Okay, and in chapter 5. But before that, we have defined the expectation of a discrete random variable and give a formula, all right, for the computation of the expectation of a discrete random variable if it exists. Okay. All right, and for the general case, we first define the expectation of a non-negative random variable in terms of an approximation sequences of discrete random variables. Okay, and we have shown that this definition is independent of the increasing sequence of discrete random variable which approximate any non-negative random variables. Okay, so and we actually give a formula to compute. Okay, such an expectation. Okay, and then we extend the expectation of a non-negative random variable to a general random variable by define the positive parts and the negative parts of a general random variable. Okay, and we know that any general random variable is the difference of its positive part, okay, to its negative part. All right. And so we define the expectation of a general random variable as the difference of the expectation of its positive part and its negative parts. Okay, so that we have actually mentioned the concept of expectation of a random variable in different chapters. Okay. Right, so we recall proposition 5.2.h that for any random variable x, the expectation of x exists, and the expectation can be computed by this formula. Okay, I provided that at least one term on the right is finite. And actually, if both terms on the right are infinite, then we say that the expectation of x does not exist. Okay, so that is a proposition we have done for that. Okay, and so also we recall proposition 5.2.j that for any random variable x, all right, with CDF f of x, the expectation of x exists. And is finite with the expectation can be evaluated by the Riemann's tetrah integral. All right, with the CDF as the integrator, and the integrand is just the linear function x. Okay, provided that the Riemann integral, so Riemann-Stieltjes integral converges absolutely, which means that this Riemann's tetrah integral is finite. Okay, right. So the integrand is just the absolute function of the linear function x there. Okay, so we can look at a simple property of expectation. Okay, if we know that random variable x is in between a and b with probability 1. Okay, so suppose that we know that the random variable has value, all right, from a to b with probability 1. All right, where a, b are finite numbers. Okay, then the expectation of x exists, and it's finite, and it also is in between a and b. Okay, so it's a very intuitive result, right? Very intuitive result. But how do we prove that? Right? So since we know that, So we know the CDF of X is here. First of all, this is 0 for all X less than A. Okay? And we know that f of X is equal to 1 for all X greater than or equal to B. Okay? You have to know that this should be strict inequality. Okay? But here is not strict. Right? X can be equal to B. Okay? Right? So this is from there. Okay. Now we first. So we would like to use this proposition. But before we are able to apply proposition 5.2.j, we have to show that the Riemann integral converges absolutely. Okay, so here, okay. Okay. Now, the Riemann integral actually is over all the x in this curse interval. Okay. Now, and we see that, so we can be upper bounded by the maxima of absolute value A and B. Okay. 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 So any x in this cross interval things so we have that, but okay, and this integral okay. All right. So this is the maxima. Okay. All right. So that's the Riemann Stieltjes integral converges absolutely, and then by proposition 5.2.j, the expectation of x okay, is equal to so this is right. So now we know A is equal to A, and okay, because this integral is equal to 1. Oh, by the way, I can write right. So maybe I just rewrite that because that non-variable x has value in between a and b. So we know that this is 0, this is constant. Okay, anyway. All right. So and so this is okay. Okay, this is the definition. Okay. All right, so right, so we have compute the expectation of a single random variables. Okay, and also we have how about expectation of functions of random variables. Okay. All right. Okay. We actually give propositions to compute expectation of functions of a single random variables. Okay, in chapter 5. Okay. How about the computation of the expectation of functions of several random variables? Okay. Now we first discussed the expectation of functions of two discrete random variables. Okay. But before that, we'll recall proposition 4.4.1. If x is a discrete random variable taking the values a sub I, and the index I is in a countable index, say capital I, and G is a real value function. Okay, so G arbitrary, okay. It can be Borel measurable or not Borel measurable, just arbitrary. Okay, when X is a discrete random variable. Then we know that it's a discrete random variable, and the expectation of g of x is equal to this expression which is provided that the sum exists where P of x is the PMF of x. All right, so so we have such a proposition to compute the expectation of a function of a discrete random variable. Okay. Right, provided that the sum exists. Okay. All right, so now we state proposition 7.2.1 point discrete. So if x and y are two discrete random variables taking the values a sub I in capital I, and b sub j in big J, respectively, and g of xy is a real valued function on R square, then g of xy is a discrete random variable, and the expectation of g of xy, x equal to the double sum of G of AI, Bj. And P is AI, Bj. Okay. And this is equal to this double sum. And we have noted that P of xy is the joint PMF of x and y. Okay. And we know P of xy is a summable function. Okay. So that the product is also a summable function. Okay, that's why this sum, by definition, is equal to this double sum. Okay. So provided that the sum exists in this statement, you have to know the gx is an arbitrary real value function, not necessarily Borel measurable. Okay, for discrete case. For general case, we require the data processing function g should be Borel measurable. Okay, but for discrete case, we can relax the requirement here. Okay, so let's prove that. Since x and y take discrete values z is equal to 2xy. Also takes discrete values. Okay? So we let C sub k be all possible values of z, where k must be a countable set. Okay? Because x and y, all right, has countably many possible values. All right, so we have that. All right. Now we let gamma k to be the set of ij pair such that g of ai bj is equal to ck. Okay, so we collect all ij pair index pairs such that after the data processing by G, AI and BJ give us CK. Okay, so this is set. Now we look at this set with all the outcomes in the sample space such that okay. And so that this is equal to such that in gamma k. Okay, so that would be the union of ij in gamma k of all the set such that and this is actually the disjoint union if you like to indicate. Okay, all right, and furthermore, so this is the intersect with okay. All right, so finally okay, so Z is equal to C sub K. Is equal to the disjoint union of all these intersections. Okay? So that this is in F. Since okay, so because X and Y are discrete random variables, so these are events of interest in the Borel sigma algebra F. And now we have doing what? We have doing intersections, countable intersections, and countable union there. Okay? So that, of course, which is a countable set. Okay? So gamma X sub K is a countable set, of course. All right, so Z equal to CK is an event of interest. So that Z is a random variable. Okay, I think it's a proposition in theorem 4. By proposition 4.2.a. Okay. Okay. So to show this is proposition 4.2.a is a position to give a necessary sufficient condition that functions defined on the sample space and have discrete values. It's a random variable, if and only if that this is set, this subset of sample space is actually a member in the sigma algebra F for every possible value. Okay. Right. So here shows that that with an arbitrary data processing function G on two discrete random variables, then the result is also a discrete random variable. Okay, so this is very general. Okay, very general. So for discrete random variable, the data processing function can be an arbitrary real value function. Okay. So any questions? Okay, now once we know that Z is a discrete random variable, then we will compute all right, so that's the PMF of Z is here. Now we compute. If the value is possible value C sub k. So now, so this is what we have. But we already show that this event is the disjoint union of the event of this joint event. So by the counteractivity of probability function, this is equal to and this is equal to the summation earthquake, right? Now we have okay. Okay, so this is P, AI, BJ. And okay, right, so we have the PMF here. Okay, so the PMF of Z, okay, can be computed by the joint PMF of X and Y, okay, with this formula. So then we have the expectation of is the K is all the Z and which is equal to K in capital K and CK and P Z CK. Okay. Okay. And for the PMF, we know this is BJ here. Okay, so we do the substitution, go to here. And now we move CK into this sum. Okay, and in here, we know the CK is equal to the G of AI and BJ. Okay, so this is become to be okay, and the G of AI BJ with P AI BJ. the double sum is actually summation for all ij in the okay, and this is what we have. So we have done. Any questions? Okay, so we take a break up to 2:20. Thank you for the correction. Okay, so that you have to correct it. Okay, this proposition state data processing on 2 discrete random variables, but it can be extended to data processing on n random variables. Okay, so let me make a remark. So proposition 7.D. For a finite number on arbitrary data processing and discrete random variables. Okay. And the proof will be the same as we have done for 2 discrete random variables x and y. All right, now we'll recall proposition so we recall a part of proposition 5.2.1. Okay. All right, so if x is an absolute continuous random variable with a PDF f of x, and g is a Borel measurable, real valued function on R, then the expectation of g of x exists and is finite with provided that the integral converges absolutely, i.e. Okay, so this is about absolute continuous case. Okay, Because G is very measurable, so of course a proposition, okay, in chapter 4 tells us that the G of X is again a random variable, okay, so this is again random, and its expectation can be expressed by this formula. We also recall proposition 6.1.c that if a data processing function is Fourier measurable, okay, real valued function on an N cell I1 then G of x1, x2, xn is a random variable for any random vector x1, x2, up to xn, whose range is contained in the N cell I1, I2, condition product to IN. Okay. So this is a result we have in the previous chapter. Okay. So now we prove the second part of proposition 7.2.1, okay, for absolute continuous case. All right, so let x and y be two jointly absolute continuous random variables with a joint PDF f of x, y, and g of x, y, a Borel measurable, real valued function on R square. Right? Then the expectation of the result of xy by the data processing function g has the expectation which is the double integral of g of xy multiplied with the joint PDF, provided that the integral exists. All right? So we let z equal to g of xy. Now from proposition 5.2.h, we have the expectation of minus okay, provided that at least one term on the right is finite. Okay? Any questions? Now, since the probability that z greater than little z, okay, so that equal to probability g of xy greater than little g, okay, so that this is equal to the double integral such that g of xy greater than little z of f of xy dx dz. Okay. So this integration is over a two-dimensional Fourier set because G is a Fourier measurable function. Okay. And proposition, the probability of this event is equal to the probability of g of xy less than equal to z. Okay. All right, and this is the double integral of all the points such that g of xy is less than equal to z. Okay. So this double integral. All right, now we evaluate. So we have the first integral. Okay, so this is the, okay, and this double integral now we exchange the order. Okay, so such that gxy is greater than 0. And here it's from 0 to g of xy. Okay. So if we exchange the order of these two integrations, okay, in this one, we do the double integral, and then after that, this is a function of z, right? And then we do the integration. This is exactly here. Okay. So we exchange the order, right? So the exchange order, so we evaluate over dz first. But the z, as we see here, that this is the case, okay? Because z is from 0 to infinity, right? So if we change the order, would be greater than 0 here, okay? And then the integration is from 0 to g of xy. Okay. Right, and this is by the Fubini theorem. Okay. Especially because the integrand is non-negative, because the joint PDF is a non-negative function. Yeah. Right, and so this becomes to be but what is that? This is exactly g of xy. Okay, so we have g of xy, f of xy, dx dy. First of all, here. And okay, so it's here, and the double integral. Okay, now we exchange the order, so we integrate. So we integrate over z first, okay? And the z, in here the z would be from minus infinity to 0, okay? So here would be g of xy, and less than equal to 0. And here is 0 to g of xy. Okay? Note that g of xy always less than equal to 0. Okay, so it's from here and there. And so that less than equal to 0. And again, this is equal to minus g of xy. Okay, this is minus g of xy. Okay. All right, and then we do the substitution back to here. Okay. Okay, so let me see where the validity of the exchange of the order of integration is guaranteed. By Fubini theorem. Since the integral integrand f of xy is non-negative. All right, so that's we have the expectation of g of xy. So when we look at minus, okay, so this term minus this minus this term. Okay, all right, and the minus sense becomes plus. Okay, so this is becomes g of xy, f of xy. Okay, and the union of these two, okay, would be in R square. Okay, because the value is either positive or non-positive. Okay? All right, so this is equal to that. Okay, so we have done here. Now the previous proposition is still valid for Borel measurable. For any Borel measurable real valued data processing function G of Rn on n jointly absolutely continuous random variables with a joint PDF. All right. All right. In chapter 4, we have exhibit a proposition about the sum of n discrete random variables. Okay. Now we'll consider linear combination of arbitrary random variables. Right? But we will separate the result into two cases. If x and y are non-negative, and A, B are also non-negative real numbers, then the expectation of AX plus BY is equal to A of X plus B of Y. Okay. The expectation of this linear combination, because this linear combination always must be non-negative. Why? Because the coefficient A and B are non-negative, and the X and Y are two non-negative random variables, so that this is a non-negative random variable, right? And so its expectation is well defined. But the expectation may be finite or infinite. Okay? The expectation of a non-negative random variable may be infinite. Okay? All right, so this expectation must exist, but may be infinite. Okay? And the equality says that even though it is infinite, it is also equal to the sum, because the sum could have finite expectation. Okay, so now, so that the, 'cause, 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 ' AB in R. Then AX plus BY has a finite expectation. And we have, again, the linear combination is equal to of X and Y is equal to the linear combination of their expectations. So for general random variables X and Y, okay, to consider their linear combinations, we require that they have finite expectations, okay, and then this linear combination also has finite expectation, okay, and then we have this equality. Okay, and so a proof will be an exercise for you. Okay, so that you just recall that we deal with the similar proposition in chapter 5 for discrete random variables. Okay, so I will give you hints when I give you an exercise of this one. Okay, so the remark. Proposition 7.2.a, okay, is true for a finite number of random variables x1, x2, up to xn together with n scalars a1, a2 up to an. Okay, so we use n scalars with n random variables to form a linear combination. Okay, and so if all these n random variables are non-negative and all the scalars are non-negative, then the expectation of the corresponding linear combination is equal to the same linear combination of their expectations. Okay, and also true if x1, x2 up to xn have finite expectations and all the scalars a1, a2 up to an are real numbers, then the linear combination they form, of course, is a random variable which should have a finite expectation. And the expectation of the linear combinations of this n random variable is equal to the same linear combination of their expectations. Okay, so that the remark says that, and the proof, okay, the proof is by induction on n. Okay, Okay, you can think about that proposition 72.2.8 is just the case for n equal to 2. Okay, and the general case for finite number of random variables, okay, can be proved by induction on n. Let x and y be two independent random variables. First of all, if x and y are non-negative, then the expectation of their product is equal to the product of their expectations. Okay? Right. For non-negative random variables, their product is also non-negative random variables. And so it must have expectation. Okay? So that this is a non-negative random variable. Okay? And so the expectation may be infinite. That's fine. Why? Because that is, if this is infinite, then one of them should be infinite, right? And any of them cannot be zero. Okay. Second, if x and y have finite expectations, then x times y has a finite expectation, and again, this finite expectation of x and y, okay, is equal to the product of their expectations. Okay? Now we prove this statement. First one. Right? So we first consider the case that x and y are non-negative, discrete. Okay, so they are discrete random variable taking a finite number values A1, A2 up to AN, and B1, B2 up to Bm, respectively. Okay, so we have a finite number of possible non-negative values there. Okay, so now by proposition, by proposition 7.2.1.d, okay, with the data processing function to be the product of x and y. So we have that expectation of x times y is equal to summation I from 1 to n, j from 1 to m of ai bj of the p ai bj. Is that okay? We just proved, right, this proposition. Okay? And AI, Bj. And because x and y are independent, so that this is equal to the joint PMF, okay, of x and y at AI and Bj is equal to the product of the marginal PMF, okay, since x and y are independent. Okay. And we have that in chapter 6, right? Chapter 6 we have let's see. And by proposition 6.2.b. Okay. So we have that. Okay. And so the sum AI, Px AI, j from 1 to n, bj, and okay. So the sum of product becomes to the product of sums here. And what is that? This is expectation of x, expectation of y. Okay. Right? So if x and y are non-negative discrete random variables, and which take finite number of non-negative values here, then we know that their expectations, the expectation of their product is equal to the product of their expectations. Okay. Any questions? In this case? No. Okay. Now for general non-negative random variables, we use approximation sequences. Now for the general case, that x and y are non-negative random variables, we let x sub n goes to x and y sub m goes to y, be sequence of non-negative. All right, so maybe I'll use B sequence of non-negative, B increasing sequence of non-negative random variables, non-negative discrete. Taking a finite number, okay, so taking a finite number of possible values such that and Okay, right? As we have done in chapter 5, right? So we can, for example, by quantization, right? By quantization, we can construct non-negative increasing sequences of non-negative discrete random variables, and each of them each of them takes a finite number of possible values, and so their limit will be go to there. All right. And then we have that x1, y1, x2, y2. Okay. Now we take their product. Okay. So we take their products, then we have that. Okay, and the limit as n goes to infinity, xn omega, I don't know, is equal to, right? Right, so we have that. Okay. Then we have the expectation of x and y is equal to the limit expectation, right? This is what we define the expectation of non-negative random variables. Okay, so the expectation of xy is equal to the limit of expectation of x and y n. But oh, I forgot here. I forgot. By quantization, okay, with that, then we have, okay, okay, so we use the quantization, right? Now, since xn is equal to okay, i.e. if the n. Okay, so we use the quantization. Right? So since x and y are independent, xn and yn are independent too. By proposition 6.3. Let's see. J. Okay. All right, so that they are independent. And then expectation of xn, yn is equal to the expectation of x times expectation of yn. Okay, so that okay. So now this expectation is the product, and because each factor has limit, so this is going to, and this is expectation of x times expectation of y. Okay, so we finished the first part. Right, and so we will continue the proof of the second part next week. Yeah, because the coming Thursday we will have the second midterm examination. Okay, so stop here.